Good morning, everyone. I'm going to start sharing the screen of my PowerPoint of today's topic, which is thermoeconomic dynamics of energy efficient orange hydrogen production, which is an energy matter. My co-authors are Ganeshan Subramanian and Praveen Kalamegan. Why is this talk? In the last year or last 2 years, we've been hearing about green hydrogen, blue hydrogen, and different forms of hydrogen. But we have to know why there are different forms of hydrogen. What does it cost to make the different forms of hydrogen? How they can be effectively, economically utilized worldwide in the quest for carbon dioxide-free hydrogen. We know there is only a limited amount of native hydrogen is found worldwide. Hydrogen is typically produced from naturally formed compounds such as water containing oxygen, hydrocarbons containing carbon, hydrogen sulfide containing sulfur. But these have to be chemically converted, applying energy and additional cost of producing the hydrogen. It is almost similar to any metallurgical production of metals, which are also usually found from oxides or from sulfides in most cases that we know of in the metallurgical industry. During 2020, worldwide, 120 million tons of hydrogen was produced, of which only 360,000 tons were produced by the green hydrogen method of electrolysis of water. Additional 1.9% came from a byproduct of chloralkali production, which is also an electrolytic method. The rest of the 97.8%, or more than 115 million tons of hydrogen, were produced by either coal gasification or steam reforming or other internally converted methods in the petroleum refineries. Why? In order to understand the why, we have to understand the basics. There are two basic equations. One is the thermodynamic energy required for a reaction, and the economic equation. We have already said these come from compounds. The compounds are depicted by H subscript P, X subscript Q, giving P by 2 molecules of hydrogen plus Q molecules of X. The thermodynamic energy is the minimum energy required, is computed from the negative value or the free energy of formation of the compound. But the actual energy in the process will be 2 to 3 times that because of the inefficiencies in the process associated with giving additional products, which may or may not be utilized. We'll come to that in the following slides. The economic equation says production cost is the sum of the raw material plus energy cost and the labor cost. Now, whenever we look at any compound from which hydrogen is made, the first two are dictated by fundamentals of thermodynamics. We in INDLLC put together this chart almost 10 months ago. This chart shows the cost of hydrogen production and carbon dioxide that is required to be sequestered for different colors of hydrogen. Because hydrogen is formed from different compounds and different methods, we just give it a color scheme. We call the native hydrogen as colorless. We can call the hydrogen produced from carbohydrates or biomatter white. Now we come to the rainbow spectrum of hydrogen colors. Over 100 years ago, some of the industrial processes produced hydrogen by reacting iron and water. It can also be done from ferrous oxide and water. Any material that's in the reduced state, which can take water as an oxidant, can produce hydrogen. This is violet hydrogen or the indigo hydrogen. And metallurgical industry can produce these kinds of hydrogen as a co-product inside their present facilities. If they have a reduced compound in their waste material, such as iron industry having iron oxide slags where iron is present in the reduced state. Even copper industry throw away some copper slags. Okay. Now comes the three major or two major production methods which you hear in the news media every day: the blue hydrogen and the green hydrogen. Natural gas steam reforming is a method that has been used for 100 years in the petroleum industry. And if you add carbon capture to it, capturing 5.5 kilograms of carbon dioxide per kilogram of hydrogen, then you produce what's called blue hydrogen. Where if you just make the electrolysis of water, which is clean, which is deionized, departiculated, and membrane clogging free, then and spend electrical energy, then we produce a green hydrogen. Then comes the yellow hydrogen, which is from hydrogen sulfide producing hydrogen or the yellow sulfur. The natural gas pyrolysis is also being talked about in the recent news media, which produces turquoise and cyan hydrogen. But in the petroleum industry, molecules containing more than one carbon atom in their hydrocarbon molecules can produce orange or red hydrogen. The orange hydrogen is a process where another hydrocarbon of use is produced along with utilizable carbon and hydrogen, whereas red hydrogen is produced by total conversion of the hydrocarbon to carbon and hydrogen. We have known for more than 150 years metallurgical coke formation produced gases that contained 50 to 60% hydrogen, which can be purified to make a 99.9% hydrogen. That we call it a brown hydrogen. Also, the new industry that was developed in the last 100 years as a competition to petroleum was the coal gasification, making transportation fuels. The coal gasification can be converted to making hydrogen, but we have to capture the carbon dioxide. This table shows the energy required to make green hydrogen is the highest, in the 48 to 80 kilowatt per kg, which compares with the 3 to 10 kilowatt per kg for orange hydrogen. Look at the last column, it shows the amount of carbon dioxide that has to be sequestered. In the case of blue hydrogen, 5.5 kgs of carbon dioxide per kg of hydrogen, and magenta, or 3 to 4 carbon dioxide per kg of hydrogen. Next slide shows the cost picture of making hydrogen by a couple of methods, which showed the water electrolysis cost 3 times as much as the natural gas steam reforming. That natural gas steam reforming did not include the cost for making carbon dioxide sequestration. We come back 45 years later to the year 2021. That was last year. We have presented the cost in euros per kg of hydrogen or dollars per kg hydrogen. Here, instead of talking in million BTUs of hydrogen, we're talking kgs of hydrogen. Only main reason for it is the recent transportation fuel cell vehicles require at least 5 kilograms of hydrogen for every refueling. It's easy to do it by weighing, and it can be consistent. Here again, you see the water electrolysis costs much more than the gas conversion. We show in this slide the amount of energy that has been added to the steam reforming to depict the carbon dioxide sequestration by these reaction equations. When you convert 1 mole of carbon dioxide to a carbon and oxygen, it takes 394 kgs, which has to be added to the reaction A and B, giving a net equation where 4 moles of hydrogen are produced for 562 kilojoules, or per mole of hydrogen, it requires 140 kilojoules by natural gas steam reforming with carbon sequestration. That is still half that of water electrolysis on a thermodynamic basis. We're not applying any other efficiency makeup energy is required in the process. INDLLC's project put together this simple thermochemistry table using Hess's principle of additivity created by Hess's law, was generated in 1840s. Here we show the free energy of formation of the compound in column 2 and compute what is the energy minimum thermodynamic required making a mole of hydrogen or a meter cube of hydrogen in kilojoules or in kilowatt hours. Knowing that there is 11.2 meter cube per kilogram of hydrogen. In the last column, we'll show the heat of formation of the compound shown in column 1. Here, you can see the heat of formation of water is 4 times the heat of formation of methane, which is a stable, methane is a stable hydrocarbon. As you go down in the alkane series, you find the numbers increasing. Better to divide those numbers by the number of molecules of hydrogen that is present in that alkane. You'll find out they are much less than that required for natural gas or methane. We touched upon methane pyrolysis, which will come to that again in the next couple of slides. Now we talk about orange hydrogen pyrolysis. Pyrolysis containing more than one carbon atom with a metastable positive free energy of formation will take the lead in future hydrogen production, along with co-products and near zero waste. Near zero waste production is called net zero. Many of the industries have been lackadaisic in considering only one product because that's what the market dictates is necessary. The other product can be thrown out. That is a simple human tendency of creating waste. Creating waste means creating heat. So if you want to reduce the warming, we have to reduce the waste. As simple as that. But some prudent industries realize that fact. Each product of a reaction has its own value and they generate markets for it. And that's how some of the giant chemical industries were formed in the last century, 1 century before that. This method, we call it met zero, method zero effluent. Method zero effluent is necessary in reducing the warming. We also note that some of the methods of making this orange hydrogen pyrolysis are already known. In 1940s, Hewell's process using direct current arc or plasma for decomposing hydrocarbons, produce hydrogen and acetylene was known. It was known and utilized in the article on coal tar pyrolysis. Another earlier industrial process of making red hydrogen along with carbon black is the carbon black and hydrogen process, which also is used to make turquoise or cyan hydrogen, which was piloted in 1992. It was shown at that time it took only 20% of the energy required compared to water electrolysis and making a meter cube or making a kilogram of hydrogen. Steiner Lanham summarized the production of carbon black and hydrogen from 1,000 kg of different feedstock. The decanted normalized number is the normalization for the same kilowatt hour, but the 1060 is the amount produced from 1,000 kilograms of the raw material stock. And this modified governor process is practiced today by Monolith Corporation in making printing ink carbon, and they have not been utilizing the hydrogen, and the recent market increase has made them start utilizing the hydrogen for that process, which they are doing by adding additional steps. They're planning a big project in the middle of America. During the 1990s, Murdoch worked on making carbon dioxide-free hydrogen with some experimental reactions using catalytic decomposition. It was published in 2003. And we are not showing some of the work that was done by Mihaly Beck in the 1990s and Franco Cataldo in the recent 20 years while studying fullerenes manufacture. Those methods are applicable for making the hydrogen. But those latter two groups were more of chemists concentrating on making fullerene, similar to the way Monolith Corporation was making printing ink as the main product, hydrogen as a co-product. But it can be converted to a combined product of net zero principles. The recent study by Marquardt indicates the BASF process being developed in Germany by Andreas Bode Group in Germany and in some of the labs in the US requires 11 kilowatt hours per kg for methane pyrolysis using induction heating instead of plasma process. There have been reports made by groups in Germany, Australia, and other places about catalytic decomposition, mainly catalytic decomposition of methane, rather than catalytic decomposition of higher hydrocarbons. Well, the catalytic decomposition of higher hydrocarbons will come into picture very soon because there is more ready infrastructure that can be easily converted and making the hydrogen for the forthcoming years. We just read this February that there is a big supply chain problem in making electrolyzers available to making the green hydrogen. Whereas converting petroleum refineries to the orange hydrogen mode with the same renewable energy resources of wind, solar, and hydro power can produce more hydrogen. What would we think will happen? The green hydrogen or the orange hydrogen? It is left to the thermoeconomic dynamics of the science. Some may call it science, spelled S-I-G-H-A-N-C-E. It's not so. Recently, Manish Sarthi's group, Dr. Angikar and others from Kaus, Saudi Arabia, have published a tabulation of yields of hydrogen from pyrolysis taking place 1000 to 1200 degrees centigrade, from surrogates of fuel oils compared with that of lower carbon containing molecules. One can see that higher yields of hydrogen is shown for molecules containing more carbon atoms. And this technology is in its infancy. Some of them have been using exotic materials costing more money without putting the cost into picture as part of science. But when it has to be satisfactory worldwide for the common public, economics will prevail along with thermodynamics. We say that again in our conclusion: the overall cost of raw material, its energy content, energy cost of conversion dictating the economics, energy cost of conversion which is dictated by thermodynamics. Once the world and the industry realize the basic thermoeconodynamics, we may find more applications of the silent orange hydrogen, which has been produced and used for over a century. Economic stability also follows thermodynamic stability and the minimization of entropy increases. Metallurgical approaches can be applied in designing refineries of the future that will be concentrating on net zero methods of hydrogen and petrochemical production using renewable energy instead of the present day transportation fuel production and petroleum refineries of the 20th century. Some of these techniques are also recompilation of technologies learned during the last century. We acknowledge the support by Indra Nilamegam in making our website, which was initiated by Praveen Kalamegam, and the website can be accessed at INDLLC.website.com/orange hydrogen. Please email questions to Nilamegam at INDLLOutlook.com.